Hello, welcome to Fresh Concrete. This is one of a series of online talks produced through partnership between the Building Centre and the Concrete Centre to showcase some of the innovative uses, manufactures and new types of concrete that are emerging, many of which are being developed to address the climate mitigation and adaptation needs of our built environment today. My name's Elaine Duguid. I'm head of architecture at the Concrete Centre, and I have had the privilege of helping to select the lineup of presenters and presentations that we have for these events. It's been fascinating. It's also been a really challenging process to select the subjects that we're going to feature. There are just so many exciting projects and products and processes being developed that we could choose from to feature in this series, all of them bringing fresh approaches and fresh thinking to concrete. So we hope that you find this presentation and you find the series as inspiring, interesting and thought-provoking as we have. So the subject of this Fresh Concrete event is carbon sequestering concrete. Now by that, I mean innovative industrial carbonation technologies developed to enhance and accelerate the carbonation of concrete. Now you may know carbonation is the naturally occurring process in which concrete absorbs carbon dioxide, permanently removing it from the atmosphere over its lifetime. Now, all concrete does this, but the rate depends on the type of concrete, the conditions to which it's exposed, and its design. So in steel reinforced structures, carbonation is designed to be limited to protect the steel reinforcement in there. And you can see from these images some samples of concrete in which the carbonation process is being tested. The grey concrete around the outside is fully carbonated. That is, it's reacted with the carbon dioxide in the atmosphere and permanently locked it into the concrete there. But the pink has yet to carbonate. And much of it is unlikely to do so, actually, until that concrete is eventually crushed or crushed for use as recycled aggregate. And it's at that point then that those new multiple surfaces of that internal concrete, shown in pink there, that they're now new surfaces are created and then newly exposed to the atmosphere, and so accelerating that carbonation process. So it's well understood, this process of carbonation, as a technical design consideration for engineers. The carbonation of concrete has, however, recently been recognised by the IPCC, that is the Intergovernmental Panel on Climate Change, as an important carbon emissions sink. And the UK government has also recognised that this process needs to be accounted for in its greenhouse gas emissions. And so it's commissioned research to develop a robust method to assess the role of concrete in the absorption of carbon across our whole built environment. And actually, we're only the second country in the world to explore this after Sweden. And so as a result of this research, it should help to improve the accuracy of UK greenhouse gas accounting. So that is a short summary of the natural process of carbonation of concrete, just to provide a bit of context for the following presentation from CarbonCure. So CarbonCure will be presenting one example of this new technology that's been developed to enhance and accelerate the process of carbonation, and it's often called industrial carbonisation. In other words, permanently locking in that carbon, but as part of the manufacturing process, so bringing it forward in that process. CarbonCure were joint winners of the NRG Cozier Carbon X Prize in 2021, joint winners together with CarbonBuilt, the focus of another Fresh Concrete recording. Each of them demonstrate a different way in which concrete can be manufactured using carbon dioxide, in doing so, reducing both the embodied carbon of the concrete, but also permanently locking in that captured CO2 emission. Deployment of these technologies to avoid and reduce carbon emissions was described by the judges of that competition as a game changer for global decarbonisation. So I would now like to introduce you to Eric Dunford, Senior Director of CarbonCure, joining us from across the pond in Canada.
All right, well, thank you, Elaine, for the introduction, and thank you as well for the invitation to participate today. So as Elaine described, I'm here to talk a little bit about our technology that we've been working on here at CarbonCure. And before I do that, I want to set the stage a little bit. I know we don't want to spend too much time talking about the challenge here. But if we look at concrete as a material and why it's such a fascinating material and why it's really important that people like Elaine are running these sessions, is that when we look at global emissions, concrete is a really large contributor, as much as 7% of annual emissions across the globe. And when you're talking about built structures, it is typically the largest source of these embodied carbon emissions. I think one thing that we often don't necessarily pay as much attention to is just the scope and scale of how much concrete there is in this world. So after water, it is the second most common material you'll encounter anywhere. And that is largely because of the fact that concrete is just a really fantastic and fascinating material that we can use for all sorts of things. So when we talk about decarbonizing construction materials, talking about concrete really matters. And that's why it's really exciting to be here to talk to you about what we're doing and also to share the stage here with Cindy and Connor from Carbon Built. So talking about CarbonCure, what is it that we actually do? CarbonCure is a technology that we provide to concrete producers that they can use to reduce the carbon footprint of their concrete products while also actually sequestering carbon into the product itself in a similar manner to the way that Elaine described it. So a key thing for you all to understand is that when I talk about our technology, we do not manufacture concrete products. So instead, we work with existing concrete producers and manufacturers across the globe. This is not something you would ever see as a CarbonCure branded product that would enter the market. We are working with existing concrete manufacturers. So our company has been around now for almost a decade. Time flies. And what we are looking at today in terms of where we are at is that we are looking at about 500 plus concrete manufacturing locations now around the globe in about 30 different countries. As Elaine described, we were fortunate enough with our co-hosts here at Carbon Built to win the Carbon X Prize in 2021. And when we talk about who we are partnered with and where this is all going, some of our investors are shown at the bottom. Important ones for us across the board, and specifically in North America anyway. One of our largest backers is the Amazon Climate Pledge Fund and the Breakthrough Energy Ventures, which is a group of individuals that are focusing on decarbonizing these materials. So that gives you a sense of the scale of the company and our trajectory. The one thing I should mention is that the first time that any of our technology was used in the field outside of the lab was approximately about 2017. So that gives you a sense of the timeline that we're talking about here for the evolution of the deployment. And looking at that map of where this is being done, these units are in Imperial, so apologies for that. Much of what we think about is American-based, based on our deployment to date. But we're talking about 18 million plus cubic yards of concrete have been manufactured with our technology to date. And that's looking at around 145 to 150,000 metric tons of CO2 reduction to date. So that gives you a sense of where some of this is happening. Most of our production to date has been in the United States, which is why you will see some of those Imperial units used in this presentation. And one thing I want to flag for you all, because this was just announced yesterday from our partners at Kilsaran Concrete in Ireland, but they are currently in the process of commissioning our technology there in the Dublin area. And they were just announcing their first truckload there being manufactured. So this is not just purely an American thing. We are actually beginning to enter some of the markets in the European Union and the Ireland and the UK. So what is our technology? What am I even talking about here? There are three things that we focus on. So two of them are just applications of concrete. So we're mostly focused on ready mix concrete, but also we have applications for precast concrete. And the third one is actually what was the source of our performance at the Carbon X Prize, which is what we call reclaimed water. I'm actually not going to spend too much time on that one today. It's kind of a secondary topic at the moment. But if you are interested in learning more about the reclaimed water technology, our website does do a pretty good job of explaining that in more detail. Looking at the ready mix application, which is what I will spend most of the time in this presentation on, that's really, again, for these trucks that you would see on the road. So any of the mixer trucks that are driving, that is the primary application of our technology today. And we're looking at that. I will get into the carbon mechanics of this, but looking at that on a per unit basis for concrete, we're talking about something like a 15 kilogram per cubic meter CO2 reduction with the current technology that has been commercialized. What you'll see kind of graded in the other technologies is there are additional CO2 benefits from those applications. And I'll explain a little bit more about that towards the end. One key thing here is following the process, I'll get into some kind of more close-ups of how this all works at the site, but this gives you kind of an infographic version of how this all happens. But what happens currently is that CO2 is sourced outside of the concrete manufacturing process. This is typically from industrial locations Places like ethanol or fertilizer plant manufacturers, CO2 is captured from those sources. It is transported to concrete manufacturing plants, and there it is used by our technology as part of the manufacturing process, all integrated with the existing production mechanism. So looking at that a bit more closely, what you are seeing here is at the plant itself. So one important consideration for any of you that are on the design side is that this technology would never appear on your projects. It is always installed at manufacturing facilities proper. So by the time the concrete leaves the yard, everything has already been accomplished, and you will not see any of this equipment show up at a job site unless you have a very large project that is using one of the portable concrete plants. This is, as I said, a retrofit technology. So we do not build new plants. We simply integrate with existing plants. The technology, as it's shown here below, kind of explains how this is going to happen. On the left-hand side, what you were seeing there is what we call the valve box, which is the control mechanism for the CO2 entering into the manufacturing process. That is attached to a tank of the carbon dioxide that is stored on the plant site, and that is what is controlling the release of that on demand. In the middle image, what you are seeing there is the control system that is inside the batch plant operator's office. That is hooked into all of their other software systems, so they can actually control the release of the CO2 based on just a click of a mouse. And on the right-hand side, what you're seeing there is the CO2 actually entering into the mixing process. So it looks a bit like a cloud. I'll explain that in a second, but you can see that there is what it often looks like inside of the mixer. This is a close-up of that right-hand image. So that is actually the injection port there where that CO2 is being introduced into the concrete. The key thing here is that that CO2 is introduced in the form of a dry ice, which is why it looks more like a snow than you might think of CO2 as a gas. This is actually being introduced in the form of a dry ice product. And the reason for that is so that it has time to undergo a chemical reaction. So if it was introduced as just a pure gas, it would want to rise to the atmosphere. So it is introduced in this way in order to enable the reaction to occur. That reaction is shown here graphically. So what happens in this mineralization reaction is effectively an industrial version of that process that Elaine was describing up front. It is happening, however, at the very onset of the manufacturing process versus over many years. And what happens here is that in the presence of water and calcium from cement, CO2 will undergo conversion where it becomes bound to that calcium as calcium carbonate. So the important part of this is that CO2 that is otherwise going to be emitted is instead redirected to the concrete plant where it is converted into this calcium carbonate solid mineral. And as a solid mineral, it means that that CO2 is no longer available to react in the atmosphere. It is instead locked inside the matrix of the concrete for hundreds of years. This is what that calcium carbonate looks like at the nano scale. So again, we're talking very, very small particles here. This is about 400 nanometers in dimension. And what is being shown here is this calcium carbonate, which looks like the sugar cube on the left, forming around calcium particles inside of the concrete itself. So you would never see this with the naked eye. It is not going to be something physically visible in concrete. It is happening at a very small scale, and it is happening distributed throughout the concrete itself. Now, the other thing on the slide that is going to probably catch your attention here, and this is kind of the interesting piece to all of this, is that what we have observed is that the introduction of mineralized carbon into concrete can also create boosts to compressive strength. So I'm going to show you an example of this. There are many examples of this that we have from our customer partners. This is an example out of the producer Hawkeye Ready Mix in Iowa. What you're seeing here again, and apologies for the imperial units, but we're looking at a design strength of 4,500 PSI. The mix design for that is shown there. What is being shown is two conditions. The original mix design that this customer of ours is using, which is shown in the black, and then the same mix design there shown in the black with the addition of CO2 on top of that. So you can see here that the strength is actually increasing versus those controls. This is, again, one customer example. There are many of these that exist, but this is just to give you an idea of what we would normally see. So the introduction of these nanoparticles of calcium carbonate does appear to increase the strength of these mixes, and that is a really important part of this whole process. So thinking along those lines, if what we know is that adding CO2 into concrete during the manufacturing stage can create the strength performance benefit, then what can we leverage that for? is higher strength concrete necessarily the desirable end state? Well, in our case, what we actually do with our partners is something a bit more convoluted, which is that those customers can leverage that increased strength efficiency to remove some quantity of cementitious material from their mixes, and then be able to deliver concrete that has the same performance and strength profile, but with less cement. So seeing here on this graph, again, this is probably the most difficult one to follow that I'll present today and the most technical. But on the left-hand side, you're seeing in these gray bars that control concrete mixes. So again, a standard baseline mix that is probably 100% Portland cement. In the middle, you are seeing in black that same mix with some quantity of cement removed from the mixture. And so that is obviously showing a lower strength profile than the original. That is what you would expect, as cement is the key strength ingredient in concrete. On the right in the orange, that is that black mixture with the reduced cement where CO2 has been added into that mixture. And what you can see there is that the goal that we work towards with our customers is to fine tune their production so that they are able to deliver concrete that meets the strength requirements, but they're doing so through a mixture of a lower cement profile and then also with the CO2 working to add strength efficiency. So that's really the two things to understand about CarbonCure and understand about this mineralization is that number one, concrete can store the CO2 beneficially early on. And then number two is that that can create opportunities for a more optimized mix design. Looking at other attributes of concrete, thinking about things like fresh or hardened properties, the other important part of all of this is that none of these other properties appear to be affected by this mineralization of the CO2. So if you want to color concrete, you can still do so. If your concerns are around freeze thaw, that does not appear to be an issue. The pH does not change. You can pump the concrete. Kind of all of the standard things you would do with concrete are still viable. From a durability lens, this is also an area that we are actively exploring today. As I mentioned, 2017 was one of the first times we would have seen this happening in practice in the real world. So we are looking at that real world data on durability and also conducting a number of studies with a number of different external partners to assess long-term durability of concrete made with carbon. In the European Union, that will be through the EN standard eventually, which we have not done to date. But here domestically in North America, we have done a number of pieces of research on this. And as you can see here, what it appears to show from all the work that has been done to date on the durability characteristics of concrete is that this mineralized CO2 is generally neutral, and in some cases might actually be providing a positive effect on some of the characteristics. So looking at the carbon reduction, again, of this current technology that we are working on in the ready-mix space, it is typically around 15 to 20 kilograms per cubic meter of concrete. So that is not a silver bullet solution. And I think you will find that in the concrete world is that there are no silver bullet solutions to removing carbon from the product. It is going to take a variety of approaches, a variety of technologies to accomplish this. And that's just there to give you a sense of where things are with this one application. With the reclaimed water technology that we are currently commercializing, we expect that figure to double to triple. So looking at some real world examples, I'm going to show you one that's a commercial building and one that is more of a paved surface. This is the Amazon's HQ2 building, which is being built just in the periphery of Washington, DC. This is their secondary headquarters on the East Coast. This project actually just topped out last week. And our technology has been used in every ounce of concrete that has gone into that building, from the flooring and the footings up to the roof. And you can see there that using this technology as part of this construction has yielded a CO2 reduction of approximately 1,043 metric tons. So this is probably one of the larger commercial buildings that we have seen. There are also a number of multi-story, tall tower buildings in Chicago and other places that are similar, but this is one of the largest commercial buildings that has been done to date. Looking at more of a infrastructure-oriented lens, this is a de-icing facility in Calgary, Alberta. So if you've never been to Alberta, one, you are depriving yourselves of seeing some fantastic glaciers and mountains, so you should definitely go check it out. But secondly, you will probably not appreciate the temperature swings that occur in this province. Calgary ranges from minus 30 Celsius in the winter to plus 35 Celsius in the summer. So it's a very demanding environment. And obviously as an airport tarmac, which is having de-icing agents sprayed on it, this is a very high stress environment for concrete. This project was completed in about 2019. You can actually read some articles on this that the engineers involved have written. but this project looking at it was done with our technology as well, and about 160 metric tons of CO2 were reduced for this one pad at the airport there. So I'm going to close my presentation here shortly, but I wanted to talk a little bit about, one of the questions we often get is, okay, I really want to help decarbonize the concrete environment. How do I do so? Again, much like I was saying in terms of the technology application, that there are going to be a number of solutions that have to work together here. I also wanted to highlight that for all of you on the line, all of us play some role in enabling innovation in this space. And that is if you are everything from a developer to a contractor, to an owner, to the actual technology company or a concrete producer, there's a role for all of us in this process. So currently, when we look at some of the behaviors and practices that are dominant in the industry, a lot of these things are actually inhibiting innovation. So things like prescriptive specifications that set minimum cement requirements, things like design RFPs that only request cost information, codes and standards are not yet mature enough to consider how CO2 utilization in concrete should be governed. I think, Elaine, you were describing that the UK government is among the first to think about that from a carbon accounting perspective. So that just gives you a sense of how early on we are in this process. And then finally, in terms of public policy and government support, there is really not a whole lot happening just yet in some of these hard to abate sectors like concrete and cement. So in the future, one thing we're all actively working towards here is if you're on the design side, then I think it would be really helpful to consider specifying performance versus minimum cement requirements, conveying your interest for lower carbon solutions to some of your service vendors that are involved in these projects. And then on the more like regulatory side and some of the more engineering sides is that we do need to spend more time on codes and standards. And we do need more supportive public policies that will help us help these industries move forward into a greener economy. So that again, that's just an overarching view of this, but I don't want to give you the sense that this is an easy thing that just using CarbonCure or Carbon Built is going to solve the whole challenge. It is very much an ecosystem-wide challenge. So with that, I am going to end my presentation. Thank you for having me join you today.
Thank you very much, Eric. And have you stopped sharing your screen now? I think you may have done. That's fantastic. Thank you. Really, really good, insightful, and absolutely to time, which is brilliant. So we have got quite a lot of questions, some quite technical ones too, so be prepared. There's clearly a lot of interest. So a few ones that have come through related to the pH, the resultant alkalinity, wondering whether, and the potential impact on reinforcement. Would you like to talk a little bit about that? Is
Absolutely.
this used for reinforced concrete, or is it still with mass concrete?
Yes, so that questioner is rightly pointing to the fact that carbon dioxide is acidic in its base compound. In our case, that conversion of the CO2 to the calcium carbonate does happen within seconds to minutes. So before it's ever exposed to steel rebar or any other reinforcement, there would be no CO2 left in the mixture in that format. So we have done studies looking at very high doses of CO2, and even at doses that are much greater than you would experience in practice, we are not seeing any decline to the pH. I did have a slide on that, should have kept it in, but very much happy to share information on that if that's helpful.
I'm sure it seems every time I talk about anything like this, it's usually the first question, especially that an engineer is going to ask on that. So absolutely right. So great. So you mentioned something there. There's also been some questions about the timing that it takes. I have a question here that says, presumably there's a period of time between that initial mixing and before there's some sufficient calcium hydroxide available for the carbonation process for when it's fully mixed. So what is the is there an average increase in the batching time needed as a result of this process?
Yeah, it's actually really not affecting the batching time process at all. It is usually added in with the trim water that is happening at the plant. So it is quite short in terms of introduction, and there is no delay in terms of the timing. So again, this is a really thermodynamically favorable reaction. It wants to occur, and it happens very rapidly, again, within kind of a minute's timeline. So we're not seeing any changes to a traditional project timeline or moving of the concrete out of the plant.
Okay, so I guess in a related question, there was one question related to the fact that it's delivered as a snow and therefore cold. I'm wondering whether that changes the mix temperature and therefore perhaps the curing time as well.
An excellent question. The volume of CO2 is not substantial enough for the mix of concrete to noticeably affect the temperature. So it is, you're very right. I mean, like a liquid nitrogen, you would assume that it would cool the concrete. It just really is not a large enough volume at that scale. We're talking about a couple of pounds per cubic yard, or a kilogram per cubic meter. So it is not enough volume of CO2 to materially affect the temperature, but you're absolutely right. And one thing that people do see is that the cold of that CO2 being introduced, it does create kind of a water vapor reaction as well on the exterior because of that cold temperature when the nozzle is actually injecting.
So that's compensated for in the mix design. That's something that becomes aware of. Yeah. Okay. Excellent. So, so the CO2 that you're using, you said it's within a cylinder. So I think because people who aren't involved with concrete, sometimes this is a bit of a confusing, or even to do with anything to do with carbon capture, this is a slightly confusing process in terms of, is it coming straight from the air outside in the batching plant? Presumably this is potentially captured CO2 from the making of cement, for example.
Yeah.
Can you talk a little bit about that potential link up?
For sure. I think I understand the question. Yes. So CO2 for us is, we don't really care where it comes from as long as it reaches a purity threshold. And I think what you'll hear, or hopefully Cindy will agree with me on this, but actually one of the major challenges to this technology application of mineralization is that carbon dioxide can be quite expensive. And based on that, we typically use CO2 sources that are the lowest price. And right now, those tend to be sources that are industrial in scale. So things like a fertilizer plant or an ethanol plant that produces very pure CO2 tends to be where the CO2 is captured today. As you're saying, Elaine, there's a really exciting research going on around whether we could capture CO2 from cement plants themselves, from the kilns. There are a lot of contaminants in those waste streams, which reduces the efficiency of that capture, which is why it's not as cost competitive with some of these other industrial sources today. But over time, at the moment, over time, I'd expect that would become more available. And similarly, there are many people working on what we would call direct air capture, where that CO2 could be pulled out of the atmosphere. And that also is quite costly today, but it's a really exciting area of research. And in theory, anyway, we could see plants in the future where they actually have these direct air capture systems on site, filling up these tanks of CO2 for use in the concrete. One of our partners in New York City is actually using CO2 sourced from the boiler systems of a residential building in Manhattan. And they're actually using that CO2 to make concrete in New York that goes to construct other buildings. So this kind of circular economy idea, I think, is going to be really exciting to see where that goes in the next couple of years.
Excellent. And the point is that it's a carbon capture technology that is then permanent. And you talked about, it's embedded there, it's mineralized effectively within the concrete. So it's using concrete as a means of being able to use that carbon dioxide. Excellent. Is there any impact on shrinkage and performance of the concrete? Do we know if it can be used in other forms of concrete, like self-compacting or lightweight concrete?
We have not seen self-compacting concrete to date, but lightweight mixtures, absolutely. We have seen that many, many times. So no, it's kind of the boring answer, but unlike all the other attributes I was talking about, things like shrinkage don't seem to be affected by the CO2. So we have seen lightweight mixes, but we have not seen, to my knowledge yet, the self-compacting concrete.
Okay. And I'm going to go through, there are so many fantastic questions here. I'm not going to be able to get through all of them. I think you mentioned that they can still be used within the concretes where there has been some cement replacements. Do you want to talk a little bit about that? So, that's that's the other ways in which one can significantly reduce the carbon footprint of concrete.
Yes.
As well.
Yeah, so this is compatible with things like a fly ash or slag. We have seen mixes of 30% fly ash and above, and then 50 to 60% slag. It has been used. Actually, the Amazon project I cited did use a large amount of slag in that project. So supplementary materials are certainly compatible with it. We've seen that with silica fume, slag, ash. We have not yet done any work with ground glass, which is an emerging pozzolan here in North America, but that's another one we're interested in seeing if they're compatible as well.
Great. So I'm going to finish off with a couple of questions here then. So we talked There's a few who are asking that if at the point at which the concrete would then be crushed, does that CO2 get re-released out into the atmosphere?
No, it's going to be permanently in there because, again, it's in that mineral format. So the only thing that's going to release the CO2 is if it hits about 1400 degrees Fahrenheit, which is the temperature that will actually split the bonds of the CO2 from that calcium. So it is permanent. And as you were saying too, Elaine, that concrete is going to continue to absorb CO2 out of the atmosphere as it normally does. So actually, what we should be doing in a lot of respects is taking that crushed concrete and pushing CO2 over it, because even in that crushed state, it will still continue to absorb CO2.
Yeah, excellent. But overall, it's absorbing more CO2 than it would do over the whole normal natural process, isn't it? That's what I'm saying. Or is it that it's just front-ending it?
It's more, I would say, front-loaded, yes, that it's kind of doing some of that work that would happen decades later up front, early on in the process.
Right, which means we can keep our concrete structures to last for hundreds and hundreds of years, which is what ideally we should be doing. And then therefore then at the end, yeah, okay, that's fantastic. And then finally, lots of questions. Is it now being used in the UK and Ireland? Are you in discussions with people? When can they see it?
Yes, so again, our Irish partner at Kilsaran is just starting to pour concrete now. So hopefully within the next few months, we will see some pilot projects springing up in Ireland. We do have partners in France. We are exploring a number of partnerships in Scotland and the UK. So you will be seeing some news on that, I'm sure, in the near term. So not today, but hopefully before the end of the year, you will be seeing some more news on that front.
Wonderful, wonderful. Well, thank you very much for your presentation, Eric. It was excellent. And thank you to everybody for all of your questions. I'm sorry that we don't have time to answer them all. But I'm sure that they can be directed directly to your company if people have some specific questions. I think.
Absolutely.
Careful what
Absolutely.
you wish for.
I welcome all questions, even if I don't know the answers to them. So okay. Thank you again for the questions, and thank you, Elaine.
Thank you very much.